Hey there everybody, we're Thalia's Harem. In this quick explanatory video, we're going to present you the difference between IPv4 and IPv6. Content here goes from history of IPv4 throughout IPv6 headers and even IP security protocols. So get yourself a popcorn and enjoy the presentation. Brief history. IPv6 was developed in 1983 and is still the most used version around the world. It consists of a 32-bit binary number, normally represented in decimal notation, with 4 digits separated by dots. For example, 255.192.0.1. That takes values between 0 and 255. This system limits IPv4 protocol to 4,000 million different addresses, which in the 80s seems to be sufficient, but in the practice it has been scarce in the result of revolution of mobile devices and imminent development of Internet of Things, which increase the number of devices connected to the network. On the other hand, IPv6 was developed in 1992, and it is widely used in densely populated Asian countries. It consists of a 128-bit binary number, so its limit is 340 sextillions of different addresses. So, why not IPv5? Until date, Internet Protocol has been recognized as IPv4 only. Versions 0 to 3 were used while the protocol was itself under development, an experimental process. Therefore, we can assume lots of background activities remain active before putting a protocol into production. Similarly, protocol version 5 was used while experimenting with the Steam protocol of Internet. It is known as Internet Stream Protocol, which used Internet Protocol number 5 to encapsulate its datagram. It was never brought into public use, but it was already used.
Let's take a look at the overview. One of the most important features of IPv6 is its extended addressing capacity. The 128 bits of an IPv6 address are represented in 8 groups of 16 bits each. Each group is written as 4 hexadecimal digits, and the groups are separated by columns. An example of this representation is as follows here in the image. As you can see, it's way larger than an IPv4 address. It also includes a global unique address indicator, a customer, a region, a subnet, a local internet registry or internet service provider, and finally the 64-bit extended unique identifier, this one right here. For convenience, an IPv6 address may be abbreviated to shortened notations by application of the following rules. One or more leading zeros from any group of hexadecimal digits are removed. This is usually done to either all or none of the leading zeros. For example, the group of 0, 1, 2, 3 could be converted to 1, 2, 3 if we want to. The other rule is that the consecutive section of zeros are replaced with a double colon. The double colon may only be used once in an address, as multiple use will render the address indeterminate. As you can see here, we use the double colon to abbreviate all this section of zeros. The IPv4 run-out is not coming as a surprise. Strictly speaking, the Regional Internet Registry (RIR) started running out of address space in 2012 and began rationing the little they had left. Fast forward a few years, and at the start of October of 2019, it was confirmed that they only had 1 million IPv4 addresses left in their available pool of 4 billion addresses in total. It is expected to run out in November of 2019. The way IPv4 requests are processed have changed over time. In 2012, each LIR could receive one 22nd IPv4 allocation in the form of a single prefix. In 2019, each LIR could receive one 22nd IPv4 allocation in the form of multiple smaller prefixes, 1/23 and or 1/24. In the future, once all available IPv4 address space is exhausted, LIRs could enter an awaiting list to receive 1/24 IPv4 allocation when addresses are returned. The total installed base of Internet of Things connected devices is projected to amount 38.6 billion devices to be connected by 2025 and 50 billion by 2030. Some segments, such as connected computing devices, will see low growth or decline, while others, such as media devices, will continue to expand steadily. Growth rates for wearable devices and connected vehicles will remain positive, but volumes will be modest relative to other segments. Address exhaustion is the main reason for switching from IPv4 to IPv6. So there were a lot of reasons that caused that. Some of them were rapid growth in the number of internet users, fast growth of mobile devices, fast growth of Internet of Things devices that wasn't expected in the 80s, and poor allocation of the addresses that we had. Some technologies like subnetting help to slow down the address exhaustion because it allows to perform a private network that connects to the internet by only one IP, but the transition to IPv6 is inevitable. That makes sense when we talk about the address space of IPv6 that provides about 5 times 10 to the 28 addresses for each people on the planet, which is the main advantage of IPv6 over IPv4.
To begin with strong differences between IPv4 and IPv6, we have the headers. The IPv6 implements improvements to make these packet headers more streamlined and more efficient for the routers to process, so they could speed the routing time. IPv6 removes optional fields from the header and put it into the package body. This makes that the header have a invariable 40-byte header length. 32 of those 40 bytes are source and destination addresses. There are not a lot of extra data in the package header. Now, let's look at each other field between packet headers IPv4 and IPv6. So, comparing IPv4 and IPv6. First, the version is going to stay the same because it is important to specify the version of the protocol. Then we have the IHL that is useless on IPv6. That makes sense because IPv6 headers always has 40 bytes. Type of service was replaced by traffic class that provides the options to establish a priority traffic. The total length is like payload length. The difference is that the total length is the entire length of the packet including the header. However, payload length is only the length of the payload excluding the header. Identification. Flags and fragment offset are functions that IPv6 doesn't need to support, so they were removed. Because those fields slow down considerably the routers. If a router receives a packet and it's too big to process it, it has options to break the packet in half, attaching a new header to both halves and forwarding the packet to the destination. And this process takes some time. In IPv6, if a router receives a packet that is too big, it throws out and sends a message to the source saying, "This package is too big." So the source resends the data in a smaller packet. Time to leave and hope limit has the same function. It is the number of routers that the packet can visit, decreased by 1 for each router that forwards the packet. The package is discarded if the jump limit is reduced to 0. Protocol defines the protocol data like TCP. In IPv6, this field was replaced by the next header and defined the type of data that is in the packet. It may also just point to the optional settings described in the top of the payload. Header checksum is a 16-bit field that is used to store checksum of the header. The receipt can use the checksum to verify if there is an error in the header. If an error was detected, it means that some bits were lost in the transmission of the packet. This has been removed in IPv6 because this function can be achieved by other OSI layer. Source and destination addresses are similar. The only difference between those was the length. In IPv4 was 32 bits, yet in IPv6 it has 4 times longer with 128 bits. IPv6 doesn't include options of padding because those are included on payload if needed.
Now let's talk about unicast, multicast, and anycast. A unicast address is used to refer to a single host. It is meant to send data to a single destination, and it's available in IPv4 and IPv6. A multicast address can be used to deliver a package to a group of destinations. Any packet sent to a multicast address will be delivered to every host that has joined the group. Since IPv6 has no support for the broadcast address, any function that used to rely on broadcasts will now be using multicast addresses. This has the great advantage of using less traffic, as only those hosts that are interested in it will join that multicast group and receive the packages. If the host hasn't joined the group, the packets will be ignored at the hardware level, not asking any resources from the operating system. And finally, the anycast address. It is very similar to the multicast address, but packets will be delivered to only one random host instead of the entire group. Anycast addresses don't have a specific range, as they are the same as regular unicast addresses. This means that a host has no way to distinguish a unicast from an anycast address when it sends a packet. It is very useful to a device that requires a wireless connection. This one needs to connect, and it doesn't care which one. It sends a kind of a broadcast to get a reply from any router that they can connect to. This is the principal function of the anycast. Hosts in IPv6 can connect to the network and assign itself his own IP address using his MAC address. This provides the capability of connecting to the server automatically with no need of DHCP. The auto configuration of an interface in IPv6 is like this. The auto configuration process creates a link local address. The auto configuration process verifies its uniqueness on a link. It also determines which information should be auto configured, addresses, other information, or both. The process determines if the addresses should be obtained through the stateless mechanisms, the stateful mechanism, or both mechanisms. As you can see, the stateless mechanism and the stateful mechanism. The determined process describes the generation of a linked local address and the process for generating side local and global addresses by stateless address auto configurations. Finally, the process describes the procedure for duplicate address detection.
Next, IPv6 stateless address auto-configuration. Stateless auto-configuration requires no manual configuration of hosts, minimal configuration of routers, and no additional servers. The stateless mechanism enables a host to generate its own addresses. It also uses local information as well as non-local information that is advertised by routers to generate the addresses. Routers advertise prefixes that identify the subnet and subnets that are associated with the link. Hosts generate an interface identifier that uniquely identifies an interface on a subnet. An address is performed by combining the prefix and the interface identifier.
In the stateful auto configuration model, hosts obtain interface addresses or configuration information and parameters from a server. Servers maintain a database that checks which addresses have been assigned to which hosts. And the stateful auto-configuration protocol allows hosts to obtain addresses and other configuration information from a server. Stateless and stateful auto-configuration complement each other. For example, a host can use stateless auto-configuration to configure its own addresses, but use stateful auto-configuration to obtain another information.
IPv6 security. New IP security protocols. Unlike IPv4, IPsec security is mandatory in the IPv6 protocol specification, allowing IPv6 packet authentication and payload encryption via the extension headers. However, IPsec is not automatically implemented. It must be configured and used with a security key exchange. IPv6 packet encryption. IPsec defines cryptography-based security for both IPv4 and IPv6 in RFC 4301 or Security Architecture for Internet Protocol. IPsec support is an optional add-on in IPv4 and is mandatory part on IPv6. It provides two security headers, which can be used separately or together. One, the authentication header or AH, and the encapsulating security payload or ESP, used in conjunction with security key exchange.
When we talk about encapsulating security payload, this provides to us a connectionless integrity, data origin notification, protection against replay attacks, unlimited traffic flow confidentiality, privacy and confidentiality through encryption of the payload. And it should be noted that IPv4 and IPv6 packets have a payload limit size of 64 KB. However, with a jumbo payload option, the IPv6 might go up to 4 GB payload. IPv4 and IPv6 transition. IPv6 is an independent parallel network. This means that it's not compatible with IPv4. Exchanging traffic between the two networks requires translator gateways using NAT64. For solution to this problem, there are three technologies. These technologies are dual stack routers, tunneling, and NAT protocol translation. In a dual stack routers, a router interface is attached with IPv4 and IPv6 addresses configured. It is used in order to transition from IPv4 to IPv6. The tunneling is this one right here. It is used as a medium to communicate the transit network with the different IP versions. The NAT protocol translation is this one right here. By the help of a NAT protocol translation technique, the IPv4 and IPv6 network can also communicate with each other. Thank you for your attention.